In the luminous heart of cosmic cities, where billions of stars pirouette in a stately, gravitational dance, lies a secret of profound darkness. At the very center of nearly every large galaxy we have ever observed, including our own Milky Way, resides an object of unimaginable density and power. It is an unseen monarch, a silent puppeteer whose influence extends across hundreds of thousands of light years. This is the domain of the supermassive black hole, a gravitational enigma that both anchors and orchestrates the grand celestial architecture surrounding it. The question that has haunted astronomers for decades is not just what these objects are, but why they are there. Why does the brightest, most crowded place in a galaxy coincide with the location of ultimate darkness? The answer is a sprawling epic, a story of cosmic birth, violent adolescence, and a surprisingly symbiotic maturity. It is a narrative that challenges our understanding of creation itself, forcing us to ask which came first, the galaxy or the monster at its core. To comprehend this cosmic mystery, we must first journey into the nature of the abyss itself. The idea of an object so massive that not even light could escape its grasp is older than one might suspect. As early as the 18th century, the English natural philosopher John Michel and later the French polymath Pierre-Simon Laplace independently conceived of what they called dark stars. Using Newtonian physics, they reasoned that a body could be so compact and massive that its escape velocity would exceed the speed of light. It was a prescient, almost fantastical idea, a ghost in the mathematical machine of classical physics. But it would take more than a century for this nascent concept to find its true, terrifying form. The stage for that transformation was set by Albert Einstein's theory of general relativity, published in 1915. Einstein presented a radical new tapestry of reality, where gravity was not a mysterious force acting at a distance, but an intrinsic curvature in the very fabric of space-time. Massive objects, he proposed, do not pull on other objects. They warp the four-dimensional ocean of space-time around them, and other objects simply follow these contours, like marbles rolling on a stretched rubber sheet. Within a year, the German physicist Karl Schwarzschild, while serving on the Russian front in World War I, found the first exact solution to Einstein's field equations. His mathematics described the space-time geometry around a single, non-rotating, spherical mass. And hidden within his elegant equations was a nightmare. Schwarzschild's solution predicted that if enough mass were compressed into a small enough volume, the curvature of space-time would become infinite. It would create a bottomless pit, a point of infinite density called a singularity. Surrounding this singularity was a boundary, a one-way membrane in the cosmos known as the event horizon. Anything that crosses this threshold, a planet, a star, a beam of light, can never return. It is the point of absolute no return. To truly visualize this, we must abandon the rubber sheet analogy and imagine something more dynamic. Picture space-time as a vast, powerful river flowing through the universe. Massive objects, like boulders in this river, cause the current to speed up around them. A planet like Earth is a small stone, creating a gentle eddy. A star like our Sun is a larger boulder, and the river of space-time flows faster in its vicinity. Now, imagine a colossal, infinitely deep waterfall. The event horizon of a black hole is like the edge of this cosmic waterfall. As you approach it in your celestial boat, the river's current, the flow of space-time itself, accelerates. At first, with powerful enough engines, you can still turn around and escape. But at a certain point, the river is flowing inward at the speed of light. This is the event horizon. Once your boat crosses this line, no matter how powerful your engines, no matter how hard you paddle, the current is too strong. The river of space-time itself is carrying you toward the singularity faster than you could ever move away. You are irrevocably swept over the falls, into an unknown oblivion. For decades, these theoretical monstrosities remained curiosities, mathematical artifacts that many, including Einstein himself, believed could not possibly exist in the real universe. Nature, it was thought, would surely have a way of preventing such a complete and total collapse. But nature, it turns out, is far more violent and extreme than we imagined. astronomers discovered that when the most massive stars, those many times heavier than our Sun, to exhaust their nuclear fuel, they can no longer support their own immense weight. The core implodes in a catastrophic collapse, triggering a supernova explosion that blasts the star's outer layers into space. What remains of the core, if it is massive enough, continues to crush itself down past the density of an atomic nucleus, past any known physical barrier, until it tears a hole in space-time and a stellar mass black hole is born. These are the common black holes, the terrifying ghosts of dead suns, perhaps tens of times the mass of our own star. But the entities residing in the centers of galaxies are an entirely different class of beast. They are not stellar mass, they are supermassive. They range from hundreds of thousands to tens of billions of times the mass of the Sunday. Our own Milky Way hosts a comparatively modest one, named Sagittarius A*, weighing in at a respectable 4 million solar masses. The galaxy Messier 87, whose central void was the first to be directly imaged, harbors a leviathan of 6.5 billion solar masses. These are not the remnants of a single star. They are gravitational titans on a scale that defies easy explanation, and their central location is the grand puzzle. Two great cosmological narratives compete to explain their origin and placement, a classic chicken and egg dilemma played out on a galactic stage. The first scenario posits that the black holes came first. In this telling, the supermassive black holes are the ancestral seeds, the gravitational nuclei around which galaxies coalesced. In the chaotic inferno of the very early universe, just after the Big Bang, conditions might have been so extreme that immense clouds of gas and dark matter could have collapsed directly, bypassing the entire life cycle of a star to form massive black holes from the outset. These primordial black holes, perhaps tens of thousands of solar masses each, would have then acted as potent gravitational anchors. Imagine the universe as a cooling, expanding fog. Within this fog, these massive seeds would be the first points of condensation. Their powerful gravity would begin to pull in the surrounding gas and dark matter, the raw materials from which galaxies are built. Just as a lustrous pearl requires an initial irritant, a single grain of sand, to begin its formation, a magnificent spiral galaxy might require a primordial black hole to serve as its core. In this model, the galaxy grows around its central engine, its structure and size dictated from the very beginning by the mass of its foundational black hole. The reason the black hole is at the center is simple. It was always there, and the center is where it created the galaxy. The second scenario flips the story entirely. It suggests that the galaxies came first. In this version, vast halos of mysterious dark matter, the invisible scaffolding of the cosmos, began to gravitationally attract ordinary matter, hydrogen, and helium gas. This gas cooled and condensed, forming the first generation of stars, and a protogalaxy was born. In this young, chaotic galaxy, there was no central monster. But the center of any gravitational system is a special place. It is the bottom of the gravity well, the point of highest density. Stars and gas clouds would naturally congregate there, creating an exceptionally crowded stellar neighborhood. Here, in this dense central cluster, a process known as dynamical friction takes hold. To understand this, picture a vast, zero-gravity trampoline representing the galaxy's gravitational potential. In this trampoline are thousands of marbles representing the stars. Now, imagine a particularly massive star or a dense cluster of stars represented by a heavy bowling ball. As this bowling ball moves among the marbles, its gravity slightly perturbs their orbits. It pulls them toward it, creating a small wake of marbles behind it. This wake of marbles exerts its own tiny, collective gravitational pull on the bowling ball, slowing it down, causing it to lose energy. As the bowling ball loses energy, it sinks deeper into the trampoline, spiraling toward the absolute center. In a young galaxy, the most massive objects, giant stars and dense star clusters, are the bowling balls. They inevitably sink to the galactic core. Once gathered at the center, this concentration of mass becomes a crucible for black hole formation. Stars might collide and merge, creating ever more massive stars that live fast and die young, collapsing into black holes. These initial black holes, themselves subject to dynamical friction, would also sink and merge. A runaway process could occur, where a small black hole swallows stars and other black holes, growing rapidly in the target-rich environment of the galactic core. Over millions of years, a seed black hole of intermediate mass emerges and settles into the very heart of the galaxy, not because it formed the galaxy, but because the galaxy's own physics forced it there. From that central throne, it could then begin its long reign of growth. Regardless of which scenario is correct, and it's possible both processes happen under different circumstances, once a seed black hole is in place, it must grow to an enormous size. This growth is driven by two primary mechanisms: accretion and mergers. Accretion is the process of feasting. The black hole's immense gravity pulls in surrounding material, gas, dust, and any star that wanders too close. This material does not fall straight in. Due to conservation of angular momentum, it spirals inward, forming a vast, flat, rotating structure called an accretion disk. This disk is one of the most extreme environments in the universe. As material gets closer to the event horizon, it orbits at nearly the speed of light. Friction and magnetic turbulence within the disk heat the plasma to millions of degrees, causing it to blaze with an intensity that can outshine all the stars in its host galaxy combined. When a supermassive black hole is in the midst of such a feeding frenzy, we call the galactic nucleus a quasar. Quasars are the lighthouses of the distant, ancient universe. Because their light is so incredibly powerful, we can see them from billions of light years away, offering us a glimpse into a time when galaxies were young and black holes were growing voraciously. The light from the most distant quasars has traveled for over 13 billion years to reach us, meaning we are seeing them as they were when the universe was less than 1 billion years old. This observation presents a profound timing problem for astrophysicists. How did these black holes grow so massive, so quickly, in the cosmic dawn? It is a major piece of evidence that favors the black hole first, or direct collapse models, as the slow, steady sinking and merging process might take too long. The other method of growth is far more dramatic: galactic mergers. Galaxies are not solitary islands, they are part of a cosmic web, and they frequently collide and merge. Over billions of years, a large galaxy like our Milky Way has cannibalized dozens of smaller dwarf galaxies. When two large galaxies, each with its own central supermassive black hole, engage in a gravitational tango, the results are spectacular. The galaxies themselves interpenetrate, their stars rarely colliding but their structures twisted and distorted by tidal forces. Vast streams of stars are flung into intergalactic space. Meanwhile, the two supermassive black holes, the heavyweights of their respective galaxies, begin a slow, inexorable spiral toward the center of the newly merged system. They shed orbital energy by flinging away nearby stars in a process of gravitational slingshotting. Eventually, after hundreds of millions of years, they find each other, forming a binary pair of supermassive black holes, orbiting each other in a final, frantic dance. They draw closer and closer, churning space-time around them, radiating stupendous amounts of energy in the form of gravitational waves, ripples in the fabric of reality itself. The crescendo of this event is their final merger, a collision that unleashes more power in a fraction of a second than all the stars in the visible universe combined. A new, more massive black hole is formed, which quickly settles into the core of the combined galaxy, ready to continue its reign, now on a grander scale. This relentless cycle of accretion and merger explains how supermassive black holes can reach their titanic proportions, but it still doesn't fully explain the intimacy of their relationship with their host galaxies. For a long time, astronomers thought of them as passive gravitational anchors, important but largely inert. We now know this is profoundly wrong. The supermassive black hole is not a parasite living in the galaxy's core. In many ways, it is the heart of the galactic organism, regulating its life and growth. This concept is known as galactic feedback. As material swirls into the accretion disk, not all of it falls past the event horizon. Incredibly powerful magnetic fields, twisted into tight coils by the disk's rapid rotation, can seize a fraction of this infalling, superheated plasma and launch it away from the black hole. These are astrophysical jets, twin beams of particles and energy, blasting out from the north and south poles of the black hole at nearly the speed of light. These jets can be immense, stretching for hundreds of thousands of light years, far beyond the visible confines of the galaxy itself. They act as cosmic blowtorches, ploughing into the interstellar gas that permeates the galaxy. This is where the feedback loop becomes critical. A galaxy's ability to form new stars depends on having a plentiful supply of cool, dense gas. If star formation proceeds unchecked, a galaxy would burn through its gas reserves relatively quickly. The jets from the central black hole act as a galactic thermostat. By blasting into the galaxy's gas clouds, they heat them up and blow them away, effectively shutting down or quenching star formation in the central regions. This is called negative feedback. The black hole's feeding frenzy prevents the galaxy from building too many new stars, ensuring it doesn't grow too large too quickly. This process elegantly explains a long-standing astronomical observation. The most massive galaxies in the universe are often red and dead, filled with old red stars and showing little to no sign of new star birth. Their central monsters have effectively sterilized them, but the feedback can also be positive. In some cases, the pressure from these expanding jets can compress gas clouds elsewhere in the galaxy, triggering new bursts of star formation in their wake. The black hole, therefore, is not just a destroyer but also a creator. It is an active participant in the galaxy's evolution, sculpting its structure, dictating its star formation rate, and shaping its ultimate destiny. This intimate connection is beautifully quantified by the M-sigma relation, a remarkable observed correlation between the mass of a galaxy's central black hole and the average speed, the velocity, dispersion, or sigma of the stars in its central bulge. It's a stunning discovery. The properties of a tiny object at the very center, occupying a space smaller than our solar system, are tightly linked to the dynamics of a structure spanning tens of thousands of light years. It is like knowing the size of a lion's heart just by measuring the speed of the outermost gazelle in its herd. This relationship is the strongest evidence we have for the co-evolution of galaxies and their central black holes. They must grow together, influencing each other in a delicate, cosmic dance that unfolds over billions of years. Of course, claiming that these objects exist is one thing, proving it is another. Since they are black, we cannot see them directly. Their existence must be inferred from their gravitational effects on their surroundings. For decades, the hunt for definitive proof was one of the holy grails of astronomy. The most compelling evidence came from watching the frantic motion of stars at the center of our own Milky Way. Two independent teams, one led by Andrea Ghez and the other by Reinhard Genzel, spent more than 2 decades meticulously tracking the orbits of stars near Sagittarius A*. Using powerful telescopes equipped with adaptive optics to correct for the blurring effect of Earth's atmosphere, they peered through the thick veil of dust that obscures our galactic center. What they found was astonishing. They witnessed stars executing complete orbits at incredible speeds, some moving at several % of the speed of light. One star, designated S2, completes an orbit in just 16 years, whipping around a central point at over 7,000 kilometers per second at its closest approach. There is nothing visible at the focal point of these orbits. The stars are performing a celestial ballet around an unseen partner. By applying Kepler's laws of planetary motion, the teams could calculate the mass of this invisible object. The answer was undeniable: 4 million solar masses, all confined to a region smaller than the orbit of Mercury. There is no known astronomical object, other than a supermassive black hole, that could contain that much mass in such a small volume. This groundbreaking work, a masterpiece of observational persistence, earned Ghez and Genzel the Nobel Prize in Physics in 2020. And yet, the ultimate proof remained elusive: a direct image of a black hole's silhouette. This seemed an impossible task. Even the largest supermassive black holes are tiny in angular size from our perspective on Earth. Imaging Sagittarius A times would be like trying to photograph a donut on the surface of the moon. No single telescope could ever have the required resolution. The solution was a planetary-scale collaboration of breathtaking ambition, the Event Horizon Telescope. The EHT is not a single instrument, but a network of radio telescopes scattered across the globe, from Hawaii to Chile, from Spain to the South Pole. Using a technique called very long baseline interferometry, all these separate dishes were synchronized by atomic clocks and digitally combined. This effectively turned our entire planet into a single, colossal lens, an Earth-sized telescope capable of achieving the necessary resolution. In April 2017, the EHT collaboration stared for days at the heart of the galaxy, Messier 87, a giant elliptical galaxy 55 million light-years away. Its central black hole is a true monster, over 1,000 times more massive than ours, making it a slightly easier, though still monumental, target. It took 2 years of painstaking data processing, using supercomputers to correlate petabytes of information, before the team was ready to unveil their result. On the 10th of April 2019, the world saw it for the first time. It was not the black hole itself, but its shadow. The image revealed a bright, lopsided ring of glowing plasma, the accretion disk, surrounding a perfect circle of pure blackness. This was the event horizon, the edge of the abyss, its size and shape matching the predictions of Einstein's general relativity with stunning precision. Here was visual confirmation, a portrait of the void. The dark heart of a galaxy had finally been brought into the light. A few years later, in 2022, the EHT collaboration released a similar image of our own Sagittarius A asterisk, confirming the monster in our own backyard. Our own supermassive black hole, Sagittarius A asterisk, is currently a slumbering titan. Its accretion disk is faint. It is not actively feeding, but it is not entirely dormant. We see occasional flares of X-ray light, evidence of small clumps of gas or unlucky asteroids meeting their doom. It is a quiet giant, but a giant nonetheless. What would it take to awaken it? If a large cloud of gas, or a star, were to be gravitationally captured, our galactic center could roar back to life as a quasar, blasting jets of energy deep into the Milky Way's halo. Such an event could profoundly alter the future of our galaxy, regulating its star formation for eons to come. We live in a calm interlude in the long and often violent life of our cosmic home. So we return to the central question: why are black holes in the middle of galaxies? The answer is a tapestry woven from threads of gravity, chaos, and time. They are there because the center is the natural gathering place for mass, the point where the seeds of destruction can be planted, either through primordial collapse or stellar cannibalism. They remain there because they are the most massive single objects, the undisputed gravitational kings of their domains. They grow there, fed by a steady diet of gas and stars, and through cataclysmic, galaxy-shattering mergers. And most importantly, they are not just located at the center, they are integral to it. They are the beating hearts that pump energy into the galactic ecosystem, the regulators that maintain a delicate balance between growth and quiescence. The galaxy and its central black hole are not two separate entities, but two components of a single, self-regulating system that has evolved together over the vast expanse of cosmic time. The dark heart of the galaxy does not just mark a location, it defines a destiny. It is the anchor and the engine, the seed and the sculptor. In its silent, crushing embrace, we find not just the end of matter, but also the organizing principle that allows 100 billion stars to call a single galaxy home. It is the ultimate paradox, the creative power of absolute destruction sitting at the very center of it all. And as we continue to peer into these luminous, swirling cities of the cosmos, we realize that we are only just beginning to understand the secrets kept by their dark and powerful rulers. The enigma remains, a silent invitation to a deeper journey into the heart of the galaxy and into the very nature of space and time itself. What if the most profound truths we hold about the universe are based on a simple cosmic illusion? Not an error in our mathematics nor a flaw in our instruments, but a deception born of our address, a celestial mirage painted on the grandest of all possible canvases. For generations we have looked out into the abyss and chronicled a story of cosmic evolution, a narrative written in the language of starlight and gravity. We believed we were impartial observers, citizens of a typical galaxy in a typical corner of space reading the universe's history as it was truly written. But a deep and unsettling mystery, a crack in the very foundation of our cosmological understanding, now forces us to ask a question as revolutionary as it is terrifying. What if our view is unique? What if our home, the magnificent Milky Way, is adrift inside a bubble of cosmic emptiness, warping our perception of everything? Our journey into this question begins here in a place of familiar beauty. You see it as a luminous, star-dusted river splashed across the darkest of night skies. This is our home galaxy, the Milky Way, a breathtaking spiral of some 400 billion suns, a swirling city of light, held together by the invisible grip of a supermassive black hole and the even more enigmatic embrace of dark matter. It is a place of violent birth and serene death, of stellar nurseries breathing fire and ancient suns fading to embers. Within one of its quiet, spiraling arms on the third planet orbiting an unremarkable star, we awaken and begin to wonder. From this vantage point, we have mapped our immediate surroundings, discovering we are not alone. Our majestic spiral is locked in a gravitational dance with the Andromeda Galaxy, both of us the dominant members of what we call the local group, a modest collection of more than 50 galaxies. For a time, this was the limit of our map, our known universe. But as our vision sharpened, our cosmic neighbourhood expanded dramatically. We learned that our local group is but a single humble suburb on the far-flung edge of an immense gravitationally bound structure, a supercluster of galaxies we have named Laniakea, a Hawaiian term for immeasurable heaven. It is a staggering congregation of 100,000 galaxies all flowing through space, together, pulled by an unseen current toward a mysterious concentration of mass known as the Great Attractor. Looking at this map, this intricate cosmic web of galactic filaments and superclusters, we felt a sense of place. We finally had an address, a line in the cosmic directory: Earth Solar System, Orion Arm Milky Way, Local Group Laniakea Supercluster. It seemed to confirm a long-held, deeply cherished assumption, a principle that underpins all of modern cosmology, the idea that we are nothing special. The universe, we believed, is on the largest scales the same everywhere. The view from our window should be more or less the same as the view from a window a billion light-years away. This is the cosmological principle, and it is the bedrock upon which our entire understanding of the cosmos has been built. And for decades that bedrock seemed unshakable. Our grand story of the universe began with a singular, explosive moment of creation, the Big Bang, an event that hurled space itself outwards in all directions. That expansion, we discovered, continues today. Galaxies are not simply sitting in a static void. They are being carried away from each other as the very fabric of space-time stretches. The central task of the modern cosmologist has been to measure the speed of this cosmic expansion, a number known as the Hubble constant. Think of it as the universe's pulse, its fundamental metabolic rate. Knowing its precise value allows us to determine the age of the universe, its ultimate fate, and the very nature of the strange dark energies that dominate it. Getting this number right is not just an academic exercise. It is the key to unlocking the entire life story of our cosmos. And to measure it, we have developed two exquisitely precise yet profoundly different methods. The first method is a journey back in time, a form of cosmic archaeology. We look to the farthest reaches of the observable universe to a time just 380,000 years after the Big Bang itself. Here we find the universe's baby picture, a faint pervasive glow of microwave radiation called the cosmic microwave background. This is the afterglow of creation, the oldest light in existence. With instruments of breathtaking sensitivity like the Planck Space Observatory, we have mapped this ancient light, revealing a pattern of infinitesimally small temperature variations. These tiny fluctuations are the primordial seeds from which all structure, including our own galaxy, would eventually grow. By feeding this data, this perfect snapshot of the infant universe, into our best tested model of cosmic evolution, the lambda CDM model, we can run the clock forward. We can calculate with astonishing precision exactly how fast the universe should be expanding today. It is a prediction forged in the fires of the Big Bang, a number derived from the universe's own pristine blueprint. This method gives us a clear, unambiguous answer for the universe's expansion rate. The second method is more direct, more local. Instead of looking back to the beginning, we look at the universe as it is now in our own cosmic era. We build what astronomers call the cosmic distance ladder, a brilliant multi-step process for measuring distances to faraway galaxies. It begins with stars in our own Milky Way whose properties we understand intimately like Cepheid variables. These are celestial lighthouses, stars that pulsate with a rhythm directly linked to their true brightness. By comparing their apparent dimness to their known intrinsic luminosity, we can calculate their distance. Once we have calibrated our measurements using these nearby stars, we extend our reach to more distant galaxies by seeking out a far more brilliant beacon, the type Ia supernova. These are the spectacular death throes of white dwarf stars, explosions so consistently and stupendously bright that they can briefly outshine their entire host galaxy. They are our ultimate standard candles. For a few weeks they blaze with a known luminosity, allowing us to measure distances billions of light years away. By measuring the distance to a galaxy and the speed at which it is receding from us, we can calculate the Hubble constant directly. This is not a prediction based on an old model. This is a direct observation of our modern universe in motion measured by legendary instruments like the Hubble Space Telescope. For years, astronomers worked tirelessly to refine both methods, certain they would eventually converge on a single triumphant number. The prediction from the early universe would match the observation from the local universe, and our model of the cosmos would be validated in spectacular fashion. But the opposite happened. As the measurements became more and more precise, the gap between the two values did not shrink. It grew. It became a chasm. The cosmic microwave background. The echo of the Big Bang predicts a universe that is expanding at a certain slower speed. The supernovae, the lighthouses of the modern cosmos, show us a universe that is expanding significantly faster by a staggering 9%. To a cosmologist, a discrepancy of this magnitude is not a minor detail. It is a crisis. It is as if a doctor measured a patient's pulse and got two wildly different readings from two different perfectly calibrated instruments. It suggests something is fundamentally wrong. The implications of this conflict, now known as the Hubble tension, are monumental. Does it mean our standard model of cosmology, the triumphant achievement of a century of science, is incomplete? Is there some new exotic physics at play in the universe? A mysterious particle or force that we have yet to imagine, something that has changed the expansion rate over cosmic time? Scientists around the world are furiously exploring these possibilities, proposing radical new ideas about the nature of dark matter and dark energy. Yet amidst this search for new physics, another perhaps more unsettling idea began to take hold. It was an idea that didn't challenge the laws of physics, but instead challenged our own place in the cosmos. It questioned the bedrock itself, the cosmological principle. What if the universe isn't the same everywhere? What if the Hubble tension isn't the result of a flaw in our model, but a bias in our location? What if we, the observers, live in a very strange place? This brings us to a question so profound it verges on the philosophical. How can we ever be sure we have a typical view? Imagine living your entire life inside a single room. You could measure the properties of the air, the temperature, the pressure, and from that you might construct a theory about the entire world's atmosphere. But what if your room happened to be a sauna? Your local measurements would be entirely accurate, but they would lead you to a completely false conclusion about the planet outside. In cosmology, we face the same potential dilemma. We are trapped in our corner of the universe, unable to step outside and see if it looks different elsewhere. Our cosmological principle has always been a powerful simplifying assumption, but it is still an assumption. And the Hubble tension may be the first piece of hard evidence that this assumption is in some subtle but critical way wrong. As astronomers began to entertain this radical notion, they looked again at the maps of our galactic neighbourhood, not just for our address, but for the character of the surrounding country. The universe on the larger scales is not a uniform sea of galaxies. It is a cosmic web. Luminous superclusters like our own Laniakea are the great filaments of this web, glittering highways of matter stretching across hundreds of millions of light years. But in between these filaments are vast, dark and profoundly empty regions known as voids. These are the great deserts of the cosmos, immense bubbles of near-nothingness where galaxies are startlingly rare. For the most part, we assumed these voids were something that happened elsewhere, that our own Milky Way was safely nestled within one of the great populated filaments of matter. Then in 2013, a team of astronomers Amy Barger, Ryan Keenan, and Lennox Cowie embarked on a meticulous project to map the density of galaxies surrounding us. They weren't looking for a solution to the Hubble tension. They were simply trying to create the most accurate three-dimensional map of our local universe ever assembled. As they pieced their data together, a truly astonishing picture emerged from the static. It revealed that the Milky Way is not in a cosmic metropolis. It is not even in a bustling suburb. The data showed with growing confidence that our galaxy and our entire local group appear to be situated deep inside one of these cosmic deserts, an immense, previously unappreciated and truly colossal underdensity in the fabric of space. It has come to be known as the KBC Void, named for the three astronomers who first charted its breathtaking scale. But a name is just a label. What is this void truly? It is not a perfect vacuum and absolute emptiness. It is rather a region of space 2 billion light-years in diameter, a bubble so vast it defies easy comprehension, that contains significantly less matter, fewer galaxies, less gas, less dark matter than the cosmic average. To say we are inside it is to say that we are living in a gravitational valley. The universe outside this bubble is denser, heavier. The great superclusters that form the void's distant walls exert a stronger gravitational pull than the sparse material within the void itself. This creates a subtle but relentless outward push. It's like being a cork in a basin of water. The water around you doesn't actively push you up, but the net effect of gravity on the denser water all around you is a buoyant force that shoves you to the surface. Similarly, galaxies inside the KBC void, including our own, would experience a local bulk outflow, a kind of cosmic wind pushing us away from the centre of the void and toward the denser structures at its edge. And in that one elegant concept, a possible solution to the Hubble tension suddenly snaps into focus. If we are being pushed by this local outflow, it would add to the overall expansion of the universe that we measure locally. It would contaminate our readings. When we observe those Type Ia supernovae to measure the Hubble constant, we would see them receding from us faster than they otherwise should. We would be measuring the global expansion of the universe plus the local effect of our void. Our measurement would be artificially inflated. It would be a celestial mirage, an illusion created by our home address. The early universe, as seen in the cosmic microwave background, would be telling us the true average expansion rate of the cosmos. But our local measurement would be telling us the expansion rate from here. And if we live in a cosmic bubble, those two numbers were never destined to agree. The audacious hypothesis was now on the table. A proposal that resolves the biggest crisis in modern cosmology not by inventing new physics, but by redrawing our map of the heavens and accepting a new, more humble and far stranger place within it. It suggests that for all our travels, for all our discoveries, we have misunderstood the very nature of our own home. But a hypothesis, no matter how elegant, is not proof. The KBC void offers a tantalizing explanation, but it raises as many questions as it answers. Is the void real? Is it large enough and empty enough to produce the effect we see? And what would it truly mean for our understanding of the cosmos and ourselves if we are to accept that we are living inside a vast, dark and lonely bubble at the edge of immeasurable heaven? The search for those answers would take us to the very limits of our observational power, forcing us to confront the universe not as we assume it to be, but as it truly is. There are moments in human history when the universe we thought we knew is utterly shattered and rebuilt in the mind of a single person. One such moment began not with a thunderous declaration, but in the profound, freezing silence of a mountaintop in the winter of 1923. There, under the colossal dome of the Hooker telescope on Mount Wilson, a lone astronomer, Edwin Hubble, found himself wrestling with ghosts on a photographic plate. For years, the world's greatest minds had been locked in a fierce debate over the nature of faint, swirling clouds of light they called spiral nebulae. Were they nascent solar systems forming within our own Milky Way cosmic weather on our celestial doorstep? Or were they something far more profound? Were they, as some dared to speculate, entire galaxies in their own right island universes, separated from us by an ocean of emptiness so vast it defied imagination? The question was the single greatest barrier to understanding our place in the cosmos. To answer it was to either confirm our majestic solitude in a single grand galaxy, or to reveal that our home was but one grain of sand on an infinite shore. Night after frigid night, Hubble guided the 100-inch mirror, a giant mechanical eye, toward the largest and most mysterious of these smudges, the Andromeda Nebula. He was hunting for a specific type of star, a celestial metronome known as a Cepheid variable. These stars are a miracle of cosmic physics. They pulsate with a precise, reliable rhythm, and the speed of their pulse is directly linked to their true intrinsic brightness. They are lighthouses in the cosmic dark. If you can measure how fast a Cepheid blinks, you know how bright it truly is. By comparing that true brightness to how dim it appears from Earth, you can calculate its distance with breathtaking accuracy. It is the universe's own measuring stick. For weeks, Hubble found nothing but the frustrating fog of distant starlight. But then, on a plate exposed in early October, he marked a suspected nova, a dying star. Upon comparing it to previous images, he realized his mistake. The star wasn't dying, it was pulsing. He crossed out the N for nova, and with a hand that must have trembled with the weight of revelation scrawled in bold letters, var, it was a variable star. It was a Cepheid. The implications of that single blinking point of light cascaded through cosmology like a shockwave. Hubble meticulously calculated the distance. The number that emerged was staggering, incomprehensible, nearly 1 million light-years. This was an order of magnitude beyond the accepted boundary of the Milky Way. Andromeda was not a cloud in our backyard. It was a sibling galaxy, a sprawling metropolis of stars as vast, as magnificent as our own, sailing in the cosmic void. In that instant, with 3 letters on a glass plate, the known universe expanded by a factor of infinity. We were not the centre of everything. We were a tiny part of a truly galactic tapestry. Humanity, in one quiet moment of discovery, was suddenly beautifully and terrifyingly humbled. Our cosmic address had been rewritten, our perspective permanently altered. We were adrift in a cosmos of galaxies, a sea of island universes stretching out in every direction, each one a potential home to billions of stars and untold possibilities. The great debate was over, but Hubble's work had just begun. He had given us a new map, and now he was about to discover the most astonishing rule that governed it. Having revealed the true scale of the universe, Hubble, now joined by the brilliant and tireless observer, Milton Humason, embarked on an even more ambitious survey. They weren't just counting the galaxies. They began to meticulously analyse the very light travelling from them. Using a spectrograph, an instrument that acts like a prism, they could break the faint ancient light from these distant island universes into its constituent colours, a rainbow barcode of its chemical makeup. And within these barcodes they found something deeply strange, a subtle but persistent distortion that would prove to be the second great cosmological revelation of the 20th century. The spectral lines of nearly every galaxy they observed were shifted. They were displaced towards the red end of the spectrum. This phenomenon, known as redshift, had a profound physical meaning. It was the Doppler effect written in starlight. Just as the siren of a receding ambulance drops in pitch, the light from an object moving away from us stretches its wavelength, lengthening, becoming redder. What Hubble and Humason were seeing was unambiguous. Virtually every galaxy in the cosmos was rushing away from us. But the discovery was more unsettling than that. When Hubble plotted his data, plotting the distance to a galaxy against the magnitude of its redshift, a stunningly simple and powerful pattern emerged. The farther away a galaxy was, the faster it was receding. This wasn't the chaotic aftermath of some cosmic explosion with debris flying randomly in all directions. This was an ordered, elegant, and universal law. It was the signature of something far more fundamental. It was the signature of space itself expanding. This was a concept so counterintuitive, so mind-bending that it bordered on the mystical. The galaxies weren't flying through space like cosmic shrapnel. The fabric of space-time itself, the very stage on which reality plays out, was stretching, carrying these galaxies along with it for the ride. Imagine dots on the surface of a balloon. As you inflate it, every dot moves away from every other dot. No single dot is the center of the expansion. From the perspective of any one dot, all the others are rushing away. This is our universe. We are not in a privileged position. An observer in any galaxy would witness the exact same cosmic exodus. This monumental idea that of an expanding reality had been predicted a few years earlier by the Belgian physicist and priest Georges Lemaître, who imagined the universe beginning as a primeval atom. But it was Hubble's painstaking observations that provided the irrefutable proof. He had found the foundational principle of modern cosmology. The universe was not a static, eternal stage as Newton and even Einstein had once believed. It was a dynamic, evolving entity with a history and a future, a story written in the stretching of light across billions of years. And like any great story, it had a pace. Hubble realized he could distill this cosmic law into a single powerful number, a constant of proportionality that connected distance and speed. This value, soon to be known as the Hubble constant, became the holy grail of cosmology. It was more than just a number. It was the universe's expansion rate, its fundamental clock speed. To measure it was to measure the age, the scale, and the ultimate fate of everything that is, was, or ever will be. Hubble's first estimate was by modern standards wildly inaccurate, but it didn't matter. He had established the principle. He had given us the key. For the next century, generations of astronomers would dedicate their lives to refining this one number, to pinning down the precise tempo of our expanding cosmos. For decades, the quest to measure the Hubble constant was a terrestrial affair, a battle waged with ever larger telescopes peering out from Earth into what we call the local universe, the galaxies within a few billion light years of us. Astronomers refined their tools, moving from Cepheid variables to a new, even more powerful kind of cosmic beacon type, EA supernovae. These are the spectacular death throes of a specific kind of star, and they explode with such a predictable, uniform brilliance that they can be seen halfway across the visible universe. They are the ultimate standard candles, our high beams for plumbing the cosmic depths. Using these supernovae, teams of scientists sharpened their measurement of the local expansion rate, narrowing the uncertainties, getting closer and closer to what felt like a final definitive answer. The number they began to converge on was about 73 kilometers per second per megaparsec. It's a strange-sounding unit, but what it means is that for every 3.26 million light-years you travel out into space, the universe is expanding 73 kilometers per second faster. This was the universe as seen from our front row seat, a measurement derived from the cosmos as it is today. But in the latter half of the 20th century, a completely different method for taking the universe's pulse was discovered, not by looking out but by looking back to the dawn of time itself. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, detected a faint, persistent, inexplicable hiss in their antenna, a noise that came from every direction of the sky with unnerving uniformity. What they had accidentally stumbled upon was the oldest light in the universe. It was the faint, fading afterglow of the Big Bang, a wall of radiation released just 380,000 years after the moment of creation, when the cosmos had cooled enough for the first atoms to form and for light to finally travel freely. This is the cosmic microwave background, or CMB. It is a baby picture of the universe. And encoded within its subtle, almost imperceptible temperature fluctuations is a treasure trove of information, a primordial blueprint containing the precise ingredients of the early cosmos, the exact amounts of dark matter, dark energy, and regular matter that would govern its evolution for the next 13.8 billion years. This discovery gave us a second, completely independent way to determine the Hubble constant. Using this pristine baby picture and our best-tested theory of the universe's evolution, the lambda-cold dark matter model physicists and cosmologists can run the cosmic clock forward. They can take those initial conditions imprinted on the CMB and with formidable mathematical precision predict what the expansion rate of the universe should be today. It is a measurement rooted not in the present, but in a prediction extrapolated from the universe's absolute beginning. and as space-based observatories like the Planck satellite measured the CMB with astonishing clarity, they produced a number for the Hubble constant of breathtaking precision. Their answer was approximately 67 kilometers per second per megaparsec. And with that result, the ground beneath modern cosmology began to tremble. Herein lies the crisis. We have two gold standard methods for measuring the expansion of the universe. One looks at the local universe around us today, using supernovae as its yardstick, and arrives at an answer of definitely 3. The other looks at the early universe, the afterglow of creation itself, and calculates that the answer must be 67. For a time, cosmologists hoped the discrepancy might be a simple error. Perhaps the measurements weren't quite as precise as we thought, but as the data poured in, the error bars on both measurements shrank until they no longer touched. Then they shrank further until they were separated by a vast, undeniable gulf. This isn't a minor disagreement or a rounding error. In the world of physics, it is a 5 sigma discrepancy, a level of certainty that signals a fundamental breakdown in our understanding. It has been called a tension, but that word is too gentle. It is a chasm. It's a paradox that strikes at the very heart of our cosmic model. It's as if you measured your child's height today and got one number, then calculated what their height should be, based on their birth records and growth charts, and got a completely different irreconcilable number. You would be forced to conclude that something is profoundly wrong with your understanding of their growth. This is the Hubble tension, and it has become the most profound mystery in cosmology today. It suggests that our grand story of the universe, from its first fiery moments to the sprawling galaxies of today, has a critical chapter missing, or a fundamental plot twist we never saw coming. The two ends of cosmic history are giving us two different answers for the same universal question. They describe two different universes, and this forces us to ask the most elemental of questions. Is our physics wrong? Is our understanding of the universe's ingredients, dark matter, dark energy, incomplete? Is there some new exotic physics at play in the cosmos, some force or particle that we have failed to account for in our models, which is altering the expansion rate in ways we cannot predict? Scientists around the world are frantically searching for this new physics, proposing radical new theories to bridge the gap. But there is another possibility, one that is perhaps simpler, yet in its own way, far more unsettling. What if our physics isn't wrong? What if our assumptions are... For a century, our entire cosmological model has rested on a foundational belief, the cosmological principle that the universe on large scales is the same everywhere. That our corner of the cosmos is average, typical, unremarkable. We have assumed that a measurement of the expansion rate made from here, from our galactic neighbourhood, is representative of the entire universe. But what if it isn't? What if our measurement of 73 is perfectly correct? For us. And what if the prediction of 67 is also perfectly correct for the universe, on average? For these two truths to coexist, it would mean that we right here, right now, are not in an average place. It would mean that our cosmic address is unusual special, and in a way that is profoundly biasing our view of the cosmos. Could it be that we live in a strange pocket of the universe, a place that is fooling us, a place that is making the galaxies around us appear to recede faster than they truly are? Before we rewrite the laws of physics, we must first be absolutely certain we understand where we are. We must interrogate our own cosmic backyard. Because it is possible, the solution to this grand cosmic paradox lies not in some exotic new theory, but in the unsettling discovery that we are trapped inside a vast invisible structure, in space, a bubble of emptiness that is warping our very perception of reality. And so, we were left with an intolerable schism, a universe split in two. One universe measured from the faint primordial glow of its own birth, expanded with a stately measured grace. The other charted by the lighthouses of nearby galaxies, and exploding stars raced outwards with an inexplicable frantic urgency. The conflict felt absolute, a paradox etched into the very fabric of space-time, suggesting that either our understanding of the cosmos's dawn or its dusk was profoundly flawed, or perhaps, just perhaps, the flaw lay not in our theories of time, but in our assumptions about space. We had assumed with an almost religious conviction that the patch of universe we inhabit is unremarkable, a typical average cosmically boring neighbourhood. The most dangerous assumption of all is the one you don't know you're making. To challenge that assumption to truly know our place, we first had to draw a map. Not a map of a city or a continent, but of everything. This was the dawn of a new kind of exploration conducted not by mariners on wooden ships, but by astronomers at the helms of colossal telescopes, the celestial cartographers of the modern age. Their quest was simple in its ambition, and staggering in its scale to chart the three-dimensional position of every galaxy they could see. For decades, our vision of the cosmos had been fundamentally flat, a beautiful but deceptive projection on the dome of the night sky. We saw galaxies as islands of light against a dark sea, but we had no true sense of the ocean's depths. The great galaxy surveys of the late 20th and early 21st centuries, like the groundbreaking Sloan Digital Sky Survey, were designed to change that forever. They were galactic census takers of an almost unimaginable scope. Night after patient night, year after grueling year, they pointed their instruments at the dark. For each faint smudge of light, they performed a delicate dissection, capturing its spectrum. Within that rainbow of information lay a secret code, the redshift. This subtle stretching of light caused by the expansion of the universe itself acted as a cosmic yardstick. The greater the redshift, the farther away the galaxy, and the faster it was receding from us. By meticulously measuring the redshift for hundreds of thousands and then millions of galaxies, astronomers began to build their map, placing one luminous pinprick after another into a vast three-dimensional digital void. They were in essence reconstructing the skeleton of the universe. And as the data poured in, as the map slowly took shape, a structure of breathtaking and entirely unexpected complexity began to emerge. The universe, it turned out, was not a uniform dispersion of galaxies, a simple dusting of stars across the infinite. Far from it. What revealed itself was a magnificent, intricate, and profoundly organic architecture, a structure we now call the cosmic web. It was as if the cosmos had woven itself into a tapestry of unimaginable proportions. Immense, rope-like filaments of galaxies billions of light-years long stretched across the darkness, twisting and connecting in brilliant super-dense knots. These knots were the great superclusters, the bustling metropolises of the universe, each a gravitational nexus containing thousands of galaxies locked in a swirling luminous dance. It was a structure of profound beauty, a cosmic nervous system where gravity was the conductor pulling matter along these shimmering pathways. But for every brilliant filament, for every dazzling cluster, the map revealed something else. Something far larger, far darker, and far more mysterious. The spaces in between. As the map grew, it became undeniably clear that the filaments and clusters were just the glittering threads of the web. The vast majority of the universe's volume was something else entirely. It was nothing. Great cavernous, almost terrifyingly empty regions we came to call cosmic voids. These were not merely gaps. They were entities in their own right, colossal bubbles of underdensity where the universe seemed to have taken a breath. Stretching for hundreds of millions of light years across these gravitational deserts were places where the cosmic census came up profoundly short. Where you would expect to find thousands of galaxies, you might find only a few dozen lonely wanderers cast adrift in an ocean of profound emptiness. The physics behind their formation is an epic tale of gravitational dominance. In the early universe, matter was spread almost perfectly evenly. But almost is the most important word in cosmology. Tiny quantum-scale fluctuations in density meant some regions were infinitesimally more massive than others. Over billions of years, gravity, relentless and patient, amplified these tiny initial advantages. The rich got richer. Matter flowed from the slightly less dense regions toward the slightly more dense ones, evacuating the spaces in between. Like water draining from a landscape, galaxies flowed downhill into the gravitational rivers of the filaments and the deep wells of the clusters, leaving behind these vast expanding basins of cosmic nothingness. The voids, therefore, are not just empty. They are actively emptying their low density, causing them to expand more rapidly than the universe as a whole, pushing the filaments and clusters further apart like a rising dough, shaping the very structure of the cosmos on the largest scales. They are the quiet, dark counterpoint to the luminous symphony of the cosmic web. For most astronomers, these voids were fascinating large-scale features of a distant universe. They were out there, a part of the grand cosmic tapestry that we observed from our comfortable and presumably average location. But in the early 2010s, a small team of researchers, Ryan Keenan, Amy Barger, and Lennox Cowie at the University of Hawaii, began to suspect this comfortable assumption might be wrong. They weren't initially hunting for a solution to the Hubble crisis. Their goal was more fundamental, a direct continuation of that grand cartographic quest. They wanted to create the most accurate and comprehensive map possible of our own local cosmic neighbourhood out to a distance of several billion light-years. They were driven by a simple nagging question: just how average are we really? Their work was a masterpiece of astronomical detective work, a painstaking process of stitching together data from dozens of different surveys, each with its own strengths and biases. They looked at surveys of galaxies in optical light, in infrared, in radio waves. They had to account for the zone of obscuration, the thick band of dust and stars in our own Milky Way that acts like a celestial fog hiding the distant universe from our view. Peering through this galactic grime required incredible ingenuity and sophisticated statistical techniques to fill in the missing pieces of the map. It was like trying to map the world from a house with dirty windows where you have to guess the shape of the landscape hidden behind every smudge and smear. Slowly, methodically, they built their model, cross-checking their findings, calibrating their distances, and gradually pushing the boundaries of the known local universe further and further out. And then they saw it. As their map became clearer, a monstrous structure began to resolve itself from the data, a feature so vast it dwarfed everything else in our cosmic vicinity. It wasn't a supercluster, a great wall, or a massive filament. It was the opposite. A void. But not just any void. This one was a titan, a behemoth of emptiness that seemed to stretch in every direction. And most unsettlingly of all, our own Milky Way galaxy, our entire local group of galaxies, appeared to be floating somewhere inside its enormous expanse. This was not some distant feature on a cosmic map. This was home. Named the KBC Void in honour of its discoverers, its scale is difficult for the human mind to process. It is a roughly spherical region of space, a bubble of profound underdensity, measuring a staggering 2 billion light-years in diameter. To put that into perspective, the light from the far side of this void began its journey towards us long before the first multicellular organisms evolved on Earth. Our own Milky Way galaxy, which we think of as an immense structure, 100,000 light-years across, is a microscopic speck of dust lost within this cosmic chasm. If you were to represent the entire void as the size of the Earth, our galaxy would be smaller than a single grain of sand. The data suggested we weren't at the dead centre of this bubble, but we were firmly, unambiguously inside it. We reside in one of the great cosmic deserts. For Keenan, Barger and Cowie, this was a stunning realisation, a discovery that fundamentally recontextualized our place in the universe. We weren't living in a typical suburban neighbourhood of the cosmic city. We were living in the rural outskirts of vast, underpopulated wilderness. But it was when they connected their discovery to the growing crisis in cosmology that the true implications began to crystallize into a radical, elegant, and deeply controversial idea. They realized that living inside such an immense underdensity wouldn't just be a matter of cosmic geography. It would have profound physical consequences. It would in fact change the way we see the universe. Imagine yourself standing on a huge, exceptionally light trampoline. All around you at the edges of the trampoline are much heavier objects. Those heavy objects will pull the fabric of the trampoline towards them. If you're standing somewhere inside that vast light area, you will feel a gentle but persistent outward tug, a pull from all sides towards the denser, heavier regions at the perimeter. The KBC void acts in precisely the same way, but with the force of gravity. The matter inside our local void is sparse, its collective gravity weak. But just outside the 2 billion light-year boundary of the void lie the colossal filaments and superclusters of the cosmic web, the Great Wall, the Shapley supercluster, immense concentrations of mass and gravitational power. These cosmic titans, forming the walls of our void, exert a powerful gravitational pull on everything inside it, including our own Milky Way. This pull is not uniform. It's an outward force tugging us and our neighbouring galaxies away from the void's relatively empty centre and toward the denser structures on its periphery. It creates a local bulk flow and extra kick, a cosmic tailwind that adds to the overall expansion of the universe. For an observer inside the void like us, this gravitational tug would be completely indistinguishable from a faster rate of cosmic expansion. We would measure nearby supernovae and Cepheid variable stars and find them moving away from us faster than they should be, because they are being pulled away by the void's massive outer walls in addition to the universe's natural expansion. The expansion isn't actually faster here, it just looks that way because we are caught in a massive gravitational outflow. We are on a cosmic river, and we've been mistakenly attributing the river's current to the speed of our boat. Suddenly, the Hubble tension was no longer a conflict between two different epochs of the universe. It was a conflict between two different locations. The measurement from the cosmic microwave background, the echo of the Big Bang, gives us the true global average expansion rate of the entire universe. It sees the forests and the trees, the filaments and the voids, and averages it all out into one single number. Our local measurements, on the other hand, are hopelessly biased by our unusual address. They are local by definition, taken from within this giant bubble, and they are contaminated by the local gravitational pull of the void's edge. We were comparing a global average to a skewed local reading and calling it a crisis. The KBC void hypothesis presented a solution of stunning simplicity. There was no need for new exotic physics. No need to rewrite our understanding of dark energy or dark matter. No need to assume that one of our two most precise sets of measurements in all of science was fundamentally wrong. All we had to do was accept a single humbling truth that we do not occupy a privileged or average place in the cosmos. We are void dwellers. Our perception of the universe has been shaped and perhaps deceived by the profound emptiness that surrounds us. It was a revelation that threatened to resolve the greatest crisis in modern cosmology by demoting our cosmic status from unremarkable to profoundly provincial. The idea was beautiful, a perfect key seeming to fit a lock that had stumped the world's greatest minds. But in science, beauty is never enough. An extraordinary claim requires extraordinary evidence. Proposing the existence of the KBC void and its theoretical effect on the Hubble constant was one thing. Proving it measuring that subtle outward flow against the torrent of cosmic expansion and convincing a deeply skeptical scientific community would be another matter entirely. The map drawn by Keenan, Barger and Cowie was the opening salvo, a declaration that the battlefield of the Hubble tension was not what it seemed. Now the real war for evidence was about to begin, a conflict that would push our observational capabilities to their very breaking point and force us to confront the true nature of our cosmic home. Faced with this deepening crisis, this schism running through the heart of cosmology, a radical, almost heretical idea began to gain serious traction. For decades, the puzzle of cosmic expansion had been approached with an implicit foundational faith that our place in the universe is on the grandest of scales, completely unremarkable. The cosmological principle, as it's known, is not just a scientific theory, it is a philosophical anchor, a declaration of cosmic modesty that has guided us since Copernicus first dared to move the Earth from the centre of everything. It insists that the view from our galactic window is given a large enough frame identical to the view from any other. But what if that assumption, that comforting belief in universal uniformity, was the very thing blinding us to the truth? What if the key to solving the Hubble tension was not to look for new physics in the distant universe, but to accept a startling new truth about our own cosmic neighbourhood? This was the moment the KBC void stepped out from the shadows of intriguing anomaly and onto the main stage as a serious contender for the throne of cosmic explanation. The theory, formally proposed by a team of astronomers including Ryan Keenan, Amy Barger and Lennox Cowie, from whose names the void gets its acronym, was both profoundly simple and breathtakingly audacious. It did not require inventing new exotic particles or rewriting the laws of gravity. It required only that we accept what the mounting evidence seemed to be screaming at us, that we live in a cosmic backwater, an immense bubble of relative emptiness. This was no longer just a curious feature on a galactic map. It was now a dynamic engine, a mechanism that could theoretically resolve the entire conflict. The core of their argument rested on a subtle but powerful consequence of Einstein's theory of general relativity. In our universe, matter and energy tell space-time how to curve, and the curvature of space-time tells matter and energy how to move. The great cosmic web, with its dense filaments and galaxy-rich superclusters, represents the colossal peaks and mountain ranges on this four-dimensional landscape. They are regions of immense gravitational pull where the fabric of the universe is cinched tight by mass. A void, conversely, is the exact opposite. It is a cosmic valley, a vast basin where space-time is stretched out, relaxed, and gravitationally weak. Imagine the universe not as a uniform expanding balloon, but as a dynamic flowing ocean with currents and tides. The superclusters are gravitational whirlpools pulling matter in. The voids, however, create a powerful gravitational undertow, but one that pushes outward. Material on the edge of a void, and even within it, doesn't feel the inward tug of a dense centre. Instead, it feels the collective pull of all the massive structures outside the void beckoning it away. This creates a net outflow, a slow but inexorable migration of galaxies away from the void's centre and towards the glittering galaxy-packed walls that define its boundaries. The KBC void theory proposed that we, the Milky Way, are caught in this very outflow. We are not just passive observers of cosmic expansion. We are surfers riding a local wave on the surface of space-time, a wave generated by the profound emptiness that surrounds us. This is where the idea of being trapped inside a bubble transitions from a poetic metaphor into a precise physical explanation for the Hubble tension. If we are inside this void, being pushed away from its centre by the gravity of the universe beyond, then our local patch of space is expanding slightly faster than the cosmic average. Think of it like being on a river. The river itself has an overall flow rate that's the global Hubble constant, the value imprinted on the cosmic microwave background from the dawn of time. But you happen to be in a particularly swift-moving channel, a local rapid. If you measure your speed relative only to the banks nearest you, you will conclude the entire river is moving at that rapid pace. You would be accurately measuring your local speed, but you would be incorrectly extrapolating it to the whole river. This is precisely what the KBC void model suggests is happening to our astronomical measurements. When we use type Ia supernovae to measure the expansion rate, we are for the most part observing stars within our cosmic vicinity, within a few billion light years. These supernovae are our nearby riverbanks. They are all caught in the same local outflow that we are. We see them rushing away from us at an accelerated rate, not just because of the universe's overall expansion, driven by dark energy, but because of this added push from the void. It's a cosmic tailwind artificially inflating our measurement of the local Hubble constant to that contentious value of 73 kilometers per second per megaparsec. Meanwhile, the light from the cosmic microwave background comes to us from the farthest edge of the observable universe, long before our void even formed. It carries the pristine signature of the global expansion rate, the true average flow of the entire cosmic river, untouched by our local anomaly. That is why it gives a value of 67. The KBC void doesn't claim either measurement is wrong. It claims both are correct, and that they are measuring two physically different things, the local rate versus the global rate. The Hubble tension in this elegant and compelling narrative ceases to be a contradiction. It becomes a confirmation of our special underdense address in the cosmos. But a compelling narrative is not enough for science. It requires proof, rigorous testing against the cold hard data of reality. And how do you test a hypothesis on the scale of a 2 billion light-year wide bubble? You cannot run a controlled experiment. You cannot step outside the void to check your measurements from a different perspective. So cosmologists turn to their most powerful tool for exploring the impossible, the supercomputer. They build entire universes from scratch digital cosmoses, born in silicon and governed by the laws of physics. This is where the KBC void theory had to prove its metal transitioning from a clever idea to a robust quantifiable model. The challenge was immense, a computational task of almost unimaginable complexity. It wasn't enough to simply simulate a void with a galaxy inside it. The simulation had to begin with the universe in its infancy, as a nearly uniform soup of matter and energy, just as it was after the Big Bang. Using these fantastically detailed initial conditions derived from our observations of the cosmic microwave background, the simulation unleashes the power of gravity. On thousands of processors running in parallel for months on end, the virtual universe evolves over 13.8 billion years of cosmic time. Billions of digital particles, each representing vast clumps of dark matter, begin to pull on each other. Tiny quantum-scale density fluctuations present from the very first moments are amplified over eons. We watch in a breathtaking time-lapse as the cosmic web weaves itself into existence. Filaments of incandescent gas and dark matter coalesce, galaxies ignite like embers along these threads, and superclusters bloom at the intersections. And just as importantly, in the spaces between the voids begin to form. They are not empty by design, but by consequence. They are the regions from which matter has been evacuated, hollowed out by the relentless pull of gravity from all sides. The simulation does not force the creation of voids. It shows them to be an inevitable and natural consequence of cosmic evolution. The crucial next step is to analyze this digital cosmos. Researchers dive into the data, searching for voids that match the observed characteristics of the KBC void, its size, its depth, its contrast with the surrounding structures. Once they find a suitable analogue, they can perform the ultimate test. They can place a virtual observer, a simulated Milky Way, deep inside this digital bubble, and from that vantage point they can program the virtual observatory to look out at its simulated sky. It can identify virtual Cepheid variable stars and virtual type Ia supernovae. It can measure their distances and their recessional velocities exactly as we do in our own universe. It can build a complete cosmic distance ladder, all within the controlled environment of the computer. The question then becomes brutally simple. Does the virtual astronomer living inside the simulated void experience a Hubble tension? The results, when they began to emerge from these colossal simulations, were stunning. In universe after universe crafted from code when a galaxy like ours was situated in a void, like the one we appear to inhabit, a discrepancy naturally appeared. The virtual observer inside the void would calculate a local Hubble constant significantly higher than the true underlying expansion rate of their simulated universe. The numbers were not just qualitatively similar, they were quantitatively precise. The models consistently produced local values clustering around 73 or 74, while the global value for the simulation remained at 67. The computer with no bias had validated the core premise of the theory. It demonstrated that a large local underdensity was not just a plausible explanation for the Hubble tension, it was a predictable consequence. The simulation showed that the gravitational effects of the void structure, the subtle push and pull on every galaxy within it, were powerful enough to create the entire discrepancy that has mystified cosmologists for years. This achievement represented a monumental turning point in the debate. The KBC void was no longer a fringe idea. It was a mathematically coherent, computationally verified model that could explain the conflicting observations without tearing down the entire edifice of modern cosmology. Yet in solving one problem, it presented a challenge to another far older concept, the very principle of our own cosmic mediocrity. To accept the KBC void is to accept that we live in a special place. Not special in a pre-Copernican sense, we're not at the physical centre of the universe, but we are in a statistically special region, a 1 in a million cosmic anomaly, a bubble of emptiness in an otherwise crowded cosmos. This proposition is for many scientists deeply uncomfortable. The cosmological principle has been an incredibly powerful and successful guide. It underpins all of our calculations about the universe's age, its evolution and its ultimate fate. To suggest that we cannot trust our local observations to represent the whole is to introduce a new and profound uncertainty. The defenders of the KBC model argue that it doesn't actually break the cosmological principle, but rather refines our understanding of it. The principle states that the universe is homogeneous and isotropic, the same everywhere and in every direction, on large enough scales. The question then is, what constitutes large enough? For decades, we assumed the scale of a few 100 million light-years was sufficient to achieve this cosmic average. The KBC void suggests that assumption might be wrong. It posits that our local neighbourhood, this bubble of influence, is far larger than we ever imagined, stretching across a staggering 2 billion light-years. Within this enormous domain, the universe is decidedly not uniform. Only when you zoom out even further to scales of many billions of light-years does our local void finally blend into the background, becoming just one of many peaks and valleys on the vast, undulating landscape of the cosmos. Our universe is still on its grandest canvas, homogeneous. We just happen to be living in one of the brushstrokes. This reframing has staggering implications. It means our position in the universe directly affects our measurement of its fundamental properties. It challenges us to disentangle the local from the global in all of our observations. Take, for instance, the mystery of dark energy. Our primary evidence for this enigmatic force comes from observing that the expansion of the universe is accelerating. That conclusion was based on measurements of distant type Ia supernovae, which appeared dimmer and thus farther away than they should have been in a universe expanding at a constant rate. But if we are inside a void, the physics of that calculation becomes vastly more complex. The outflow from the void provides an additional local acceleration to nearby objects. It acts as a sort of mimic, a phantom force that could be mistaken for the effects of dark energy, or at least be conflated with them. The KBC model forces us to ask a difficult question: how much of the cosmic acceleration we attribute to dark energy is actually just a local illusion, a trick of the light created by the gravitational valley in which we reside? Some of the most extreme interpretations of the KBC void's influence suggest it could account for a significant portion of the observed acceleration, potentially reducing the amount of dark energy needed to explain the cosmos. While most researchers believe dark energy is still very real, the void introduces a major systematic effect that must now be accounted for in all future measurements. It complicates the story, adding a new layer of celestial clockwork that must be understood before we can truly claim to know the fate of our universe. The bubble we're in does more than just speed things up. It warps our very perception of cosmic destiny. It hangs a veil between us and the universe beyond a veil, woven from gravity and emptiness. To truly solve the deepest mysteries of the cosmos, we first have to find a way to see past the distorting lens of our own cosmic home. The search for confirmation for a definitive test that could prove or disprove our residency in this great void was now on. We had a map, a theory, and a motive. All we needed was a smoking gun. And so the model was built. A ghost in our cosmic backyard. A bubble of emptiness stretching for 2 billion light years, with our Milky Way galaxy adrift somewhere inside its desolate expanse. This gargantuan structure, the KBC void, offers a breathtakingly elegant, almost deceptively simple solution to the Hubble tension. It suggests that for the past 2 decades, we weren't measuring a flaw in our physics, but merely a flaw in our perspective. From within this great underdensity, the universe beyond would naturally appear to be flying apart faster than it really is, a cosmic mirage born from the gravitational pull of the denser cosmos that surrounds us. The crisis could be over. The tension could be resolved. But in science, a solution that seems too perfect often conceals a far deeper and more unsettling problem. By potentially solving one cosmic mystery, the KBC void forces us to confront a paradox that strikes at the very heart of our entire understanding of the universe's history and its ultimate architecture. The question is no longer just about measurement, it has become about creation itself. To grasp the magnitude of this new dilemma, you have to rewind the clock, not just by years or millennia, but back through the unimaginable deep time, back to the very first moments after the Big Bang. Our standard model of cosmology, the triumphant lambda CDM model, is built upon a foundational principle. The universe began in a state of almost perfect, almost featureless uniformity. The evidence is imprinted in the oldest light we can see, the cosmic microwave background. It shows us a baby universe where the density from one point to another varied by only 1 part in 100,000. These were the seeds of everything. Tiny quantum-scale whispers of variation in an otherwise smooth primordial soup. Over the next 13.8 billion years, gravity went to work on these seeds. It was a slow, patient, and relentless process. Regions that were infinitesimally denser than their surroundings began to pull in more matter, their gravitational influence growing stronger with every particle they accrued. Dark matter, the invisible scaffolding of the cosmos, formed vast ethereal halos. These halos in turn became the gravitational anchors that drew in ordinary gas, igniting the first stars and forging the first galaxies. Over eons, this process sculpted the universe into the grand structure we see today, the cosmic web. It is a luminous, intricate tapestry of galaxy filaments and superclusters woven across the darkness of intergalactic space. And just as crucial to this tapestry are the empty spaces between the threads, the great cosmic voids. The lambda CDM model doesn't just allow for these voids, it demands them. They are the natural, inevitable consequence of gravity piling matter up elsewhere. Our supercomputers running simulations that evolve virtual universes from the Big Bang to the present day consistently produce this web-like structure. They show us a cosmos filled with voids of all different sizes. But here lies the terrifying complication. There are voids, and then there is the KBC void. According to the vast majority of our cosmological simulations, a structure as monumentally large and as profoundly empty as the KBC void should be an extraordinary rarity. It's like walking across a beach and finding a single grain of sand the size of a house. It's not that the laws of geology forbid it, but its existence would scream that some unknown powerful process was at play in its formation. The KBC void is that house-sized grain of sand. It is a statistical outlier of the highest order, a feature so extreme that its very presence on our cosmic doorstep feels less like a random fluctuation and more like a deliberate statement. The standard model predicts a universe where such colossal underdensities are so improbable that finding one, let alone living inside it, borders on the impossible. This forces us to a chilling crossroads. Either we are the beneficiaries of a cosmic lottery win of unimaginable improbability, a statistical fluke so rare it might only happen once in the observable universe. Or the model is wrong, not just slightly incomplete, but fundamentally missing a key piece of the cosmic puzzle. The existence of the KBC void could be whispering to us that the forces that sculpted the universe are not quite what we thought they were. It may be evidence for new physics. This is where the story pivots from a problem of measurement to a profound quest for the unknown laws of nature. If the standard model cannot comfortably accommodate a void of this scale, then we must ask what kind of force, what kind of energy, what kind of primordial event could carve out such a staggering chasm in the fabric of the cosmos? One of the most audacious possibilities is that we have misunderstood gravity itself. Einstein's theory of general relativity has been our guide for over a century, passing every test we have thrown at it with flying colours. But it has been tested most rigorously within the solar system and among stars and galaxies. Perhaps on the truly gargantuan scales of superclusters and cosmic voids, gravity behaves differently. Some theories of modified gravity propose that on these immense scales, the force could become repulsive, actively pushing matter away and exaggerating the growth of voids to sizes far beyond what standard gravity would permit. If this were true, the KBC void would no longer be a statistical anomaly. It would be an expected feature of a universe governed by a more complex, more complete theory of gravity. The implications are almost too profound to fully comprehend. It would mean that the cosmic acceleration we attribute to dark energy might just be an illusion, a grand-scale manifestation of gravity flipping its own script. Another tantalizing avenue of exploration lies in the nature of dark energy. In our standard lambda CDM model, dark energy is the lambda, the cosmological constant. It is a simple, unvarying background energy woven into space-time itself, causing the expansion of the universe to accelerate at a steady, constant rate. But what if dark energy is more dynamic? More volatile? Some physicists theorize about something called quintessence, a form of dark energy that can change over time and vary from place to place. Perhaps in the early universe this energy wasn't uniform. Maybe there were domains or bubbles of a different kind of dark energy, an energy that didn't just push everything apart equally, but actively worked to hollow out certain regions like a celestial blowtorch excavating vast caverns in the developing cosmic web. A void like KBC could be the ancient scar of such an event, a relic from a time when the cosmic rulebook was far stranger than we imagine. Or perhaps the answer lies even further back in the very first fraction of a second after the Big Bang during the period of cosmic inflation. We believe inflation smoothed out the universe but left behind the tiny quantum fluctuations that seeded all structure. Our models assume these seeds were random and followed a simple statistical pattern. But what if they weren't? What if, in addition to the common small-scale fluctuations, the inflationary process also produced incredibly rare but massive primordial fluctuations? What if the blueprint for the KBC void was written into the universe before it was even a second old, a vast preordained region of slightly lower density, fated from the very beginning to grow into the abyss we now find ourselves in. This idea, known as primordial non-Gaussianity, would mean that extreme structures, both massive superclusters and colossal voids, are more common than the standard model predicts. The void wouldn't be a fluke. It would be a feature, a clue pointing back to the exotic physics that governed the universe's birth. Each of these possibilities, modified gravity dynamic, dark energy, primordial seeds, represents a monumental departure from established cosmology. They are not simple tweaks to the existing model. They are revolutions. And the KBC void, this quiet, empty patch of space, could be the silent witness that testifies to their reality. But in the grand arena of science, no revolutionary idea goes unchallenged. For every cosmologist intrigued by the void as a portal to new physics, there is another who urges caution, demanding more evidence, and rigorously scrutinizing the foundations of the claim itself. The debate over the KBC void is a perfect illustration of the scientific method in its purest form, a relentless, sometimes brutal process of skepticism and verification. The first line of attack from the critics is always the most fundamental one. Are we sure the void is even there? Or at least is it as large and as empty as the KBC team claims? Mapping a three-dimensional structure that is 2 billion light-years across is an undertaking of staggering complexity. It relies on piecing together data from dozens of different galaxy surveys, each with its own potential biases, blind spots and systematic errors. Counting galaxies to determine density is notoriously difficult. Dust within our own Milky Way can obscure our view, making distant regions appear emptier than they truly are. Some types of galaxies are faint and harder to detect than others, potentially leading to undercounts in certain directions. The critics argue that if you look at the sky with different surveys using different methods to measure galaxy distances and densities, the evidence for a single coherent spherically symmetric void centered on us begins to look less robust. Some studies suggest that what we perceive as one giant void might actually be an alignment of several smaller, less extreme voids, a chance arrangement that creates the illusion of a single monolithic structure. If the void is smaller or less empty than initially proposed, its ability to resolve the Hubble tension diminishes significantly, and its challenge to the standard lambda CDM model largely evaporates. It would revert from being a house-sized grain of sand back to just a large but perfectly plausible pebble on the cosmic beach. This is the most conservative and for many the most likely explanation. Before we tear down our most successful theory of the universe, we must be absolutely certain we haven't just made a mistake in our observations. Furthermore, even if the KBC void is real and does resolve the Hubble tension, it is by no means the only game in town. The cosmological community is buzzing with other potential solutions to the crisis, many of which do not require us to be in a special place in the universe. These alternative theories focus not on our local environment, but on changing the physics of the early universe. One of the most popular is the idea of early dark energy. This model proposes that in the first few 100,000 years after the Big Bang, there was an extra temporary burst of dark energy. This would have subtly changed the physics of the plasma in the early universe, altering the size of a key feature called the sound horizon that is imprinted on the cosmic microwave background. Our calculation of the Hubble constant from the CMB relies on measuring this feature. If early dark energy made the sound horizon smaller than we think, then our calculation would be off. When corrected, the value derived from the early universe would snap into agreement with the value we measure locally today. No void needed. No special location required. Another path involves tinkering with the fundamental particles that filled the cosmos. What if there were other undiscovered particles whizzing around in the primordial plasma? Perhaps a new type of neutrino, a so-called sterile neutrino, or other forms of dark radiation. These extra ingredients would have changed the universe's energy budget in its youth, altering its expansion rate in a way that could once again reconcile the measurements from the beginning of time with those made today. And then there is the simplest and perhaps least exciting possibility of all. That the tension is not a sign of new physics, but a result of yet unidentified errors in one or both of the measurements. The teams measuring the local expansion rate using supernova and Cepheid stars have spent years refining their techniques, hunting for every conceivable source of error. The teams analysing the cosmic microwave background with the Planck satellite have performed one of the most precise experiments in the history of science. Both are among the most meticulous and respected groups in the world. But science is a human endeavour, and the universe is a messy place. The possibility remains that some subtle, unaccounted-for effect, some quirk in the behaviour of Cepheid variable stars, some misinterpretation of galactic dust, some minute instrumental bias in a satellite is leading us astray. This is the landscape of the debate, a complex, multifaceted puzzle with clues pointing in radically different directions. On one side, a giant local void, an explanation that is both geographically simple and cosmologically radical. On the other, a suite of alternatives that preserve our cosmic modesty, but demand new physics in the universe's distant past, or the sobering possibility of a simple human error. The scientific community is locked in this grand investigation, with every new piece of data, every new analysis being placed on the scales, weighing the evidence for and against each competing hypothesis. The KBC void is no longer just a curious feature on a galactic map. It has become a focal point for the biggest questions in cosmology. Is it a phantom, a ghost, in the data that will vanish with more precise observations? Or is it a genuine titan, a structure so vast that its gravitational influence has been misleading us for decades? Is it a harmless anomaly, a statistical curiosity that our standard model can in the end accommodate? Or is it the key that will unlock a door to a new undiscovered realm of physics, forcing us to rewrite our cosmic creation story from the very first chapter? Finding the answer will require a new generation of cosmic explorers armed with more powerful eyes and more ingenious methods than ever before. The evidence we have gathered so far has led us to this profound uncertainty. To move forward, we must push deeper into the void itself and listen more closely to the echoes from the dawn of time. The final verdict on our place in the cosmos is waiting to be read, and the next chapter in this story will be written by the light from a billion distant galaxies. And so the time for mere theory has passed. The grand and unsettling proposition of the KBC void, this colossal underdensity in which we may be unwitting residents, has been placed upon the cosmic scales. On one side sits the foundational pillar of our cosmological understanding, a smooth, uniform universe, elegantly described by the standard model. On the other, this audacious, almost heretical idea of a local bubble, a gravitational valley warping our view of everything beyond. The debate can no longer be won with elegant mathematics or persuasive argument alone. It has graduated from the chalkboard to the observatory, becoming a war of observation, a high-stakes campaign for data so precise, so unambiguous, that it can either shatter the void hypothesis forever or force us to rewrite the very first chapter of the universe's story. The question is no longer just if we live in a void, but how we can build an ironclad case for its existence, a case that can withstand the fiercest scientific scrutiny. We are now entering the final decisive phase, the hunt for the smoking gun. To prove we are adrift in a cosmic basin, we must first map its contours with an almost impossible exactitude. For decades, charting such a structure was a task of immense painstaking labour, akin to mapping an entire continent using only a rowboat and a sextant. Astronomers would point their telescopes at tiny patches of sky-counting galaxies one by one, slowly, painstakingly building a picture of the local cosmos. But now, we have entered an era of celestial cartography on an industrial scale. Surveys like the Sloan Digital Sky Survey have acted as our trailblazers, creating vast three-dimensional atlases of the universe, revealing the gossamer threads of the cosmic web and the stark emptiness of the voids that stretch between them. These maps gave us the first tantalizing hints, the initial blurry outlines of the KBC void, confirming that our galactic neighborhood is indeed sparser than average. Yet these static maps, these mere counts of galaxies, are not enough. They show us where things are, but the ultimate proof lies in determining how things move. Every galaxy you see is a participant in a grand cosmic ballet, a dance choreographed by gravity over billions of years. The dominant movement, of course, is the majestic expansion of space-time itself, the Hubble flow carrying everything away from everything else like raisins in a rising loaf of bread. This is the universe's overwhelming uniform motion. But superimposed upon this grand expansion is a far more subtle and intimate performance, the peculiar velocity. This is the personal individual motion of a galaxy, its private drift and tumble through space, dictated not by the expansion of the universe, but by the gravitational pull of its immediate neighbours. It is the slight sidestep in the cosmic waltz, the deviation from the lockstep march of cosmic expansion. A galaxy might be pulled towards a massive unseen cluster, or pushed away by the desolate emptiness of a void. These peculiar velocities are the whispers against the roar of the cosmos, and within them lies the key. If the KBC void is real, it cannot hide its influence. Its immense gravitational deficit, its relative lack of matter, must be exerting a powerful and measurable repulsive force, a cosmic outflow and exodus from the emptiness. We in the Milky Way, along with our entire local group of galaxies, should be feeling this push. We should be surfing a gravitational wave away from the void's centre, moving faster than the Hubble flow alone would predict. Measuring this delicate, localized motion across hundreds of millions of light years is the critical test, the Herculean challenge now facing astronomers. It is an attempt to detect a gentle cosmic breeze while standing in the heart of a hurricane. To catch these fleeting gravitational whispers requires tools of extraordinary sensitivity. Astronomers have devised ingenious methods, cosmic distance ladders, built not on supernovae, but on the intrinsic properties of galaxies themselves. For spiral galaxies, they employ the Tully-Fisher relation, a remarkable correlation between a galaxy's luminosity and the speed of its rotation. By measuring how fast the stars in its arms are swirling, a feat accomplished by analysing the Doppler shift in their light, we can deduce the galaxy's true intrinsic brightness. Comparing this to how bright it appears from Earth gives us a precise distance independent of its redshift. For the great elliptical galaxies, the ancient spherical cities of stars, a similar tool exists known as the fundamental plane. It connects a galaxy's size, its surface brightness, and the chaotic random motions of its stars into a single reliable equation. Again, by measuring these properties, we can calculate a true distance. Once we have this true distance, we can calculate what its velocity from cosmic expansion should be. The final step is to compare that expected velocity to the actual velocity we measure from its redshift. The difference, that tiny, almost imperceptible mismatch, is its peculiar velocity. It is the fingerprint of local gravity, the telltale sign of a push or a pull from some unseen structure. For years, teams around the world have been painstakingly compiling catalogues of these motions, creating maps not of galactic positions, but of their secret journeys. The Cosmic Flows Project, a monumental undertaking, has assembled the largest ever collection of peculiar velocity measurements, revealing the intricate network of gravitational currents that define our cosmic supercluster Laniakea. These maps show us the great rivers of galaxies flowing towards the Great Attractor, a colossal gravitational anomaly, and other massive structures. But they also reveal something else, something more subtle, a coherent bulk flow, a large-scale motion of our entire cosmic neighbourhood that seems to align disturbingly well with the predicted outflow from the KBC void. The evidence is suggestive, deeply compelling, but still not definitive. The uncertainties in these measurements, the sheer difficulty of untangling a tiny local motion from the universe's colossal expansion over such vast distances, leave room for doubt. The data is noisy, the error bars just large enough for skepticism to find a foothold. What we need is a new generation of eyes, a quantum leap in our ability to chart these cosmic tides. And that new generation is at last arriving. On the horizon, 2 new sentinels are preparing to take their watch, 2 revolutionary observatories designed to map the universe with a breadth and depth that will make all previous surveys look like preliminary sketches. The first is the European Space Agency's Euclid telescope. Euclid is not designed to stare intently at single objects. It is a cosmic surveyor, a grand cartographer of the dark. Over 6 years, it will systematically scan over 1/3 of the entire night sky, imaging billions of galaxies and measuring their properties with unprecedented precision. Its primary mission is to understand the nature of dark energy and dark matter by mapping how the universe's structure has evolved over time. But as a direct consequence of this mission, Euclid will create the most extensive and detailed 3D map of the cosmos ever conceived. It will chart the KBC void not as a blurry region of absence, but as a well-defined structure with sharp boundaries and a precisely measured density profile. It will provide the definitive atlas against which all theories must be compared. Is the void a simple, smooth depression, as the current model suggests, or is its structure more complex? Euclid's data will be the bedrock, the foundational map that transforms our investigation. Following closely behind is NASA's Nancy Grace Roman Space Telescope, a machine with the panoramic vision of Hubble, but a field of view 100 times wider. Roman is a master of cosmic demographics built to conduct galactic censuses on an unimaginable scale. While Euclid maps the grand structures, Roman will conduct a different kind of survey, one that strikes at the very heart of the Hubble tension. It will hunt for type Tsea supernovae, those glorious standard candles with ruthless efficiency. Where previous surveys might have found hundreds over several years, Roman is expected to discover tens of thousands. This enormous statistical sample will allow us to measure the expansion rate of the universe in our local environment, the very measurement that clashes with the cosmic microwave background to a staggering new level of precision. It will test the other side of the equation. Euclid will define the void's physical reality, while Roman will nail down its apparent effect on the Hubble constant. Together they form a cosmic pincer movement attacking the problem from two directions. One telescope will map the cause, the underdense bubble, while the other will precisely measure its alleged effect, the faster local expansion. If the data from these two behemoths align, if the detailed map of the void from Euclid perfectly predicts the anomalous Hubble value measured by Roman, the case for the KBC void will become nearly unassailable. Yet even this two-pronged assault may not be the final word. There is another more ethereal form of evidence we can seek, a ghostly imprint left on the oldest light in the universe. We can look for the void's signature not in the light from galaxies within it, but in the ancient radiation of the Big Bang that passes through it. This is the cosmic microwave background, the faint omnipresent afterglow of creation, a baby picture of the universe when it was just 380,000 years old. This light has been travelling towards us for 13.8 billion years, and its journey has not been uneventful. As it traverses the vast structures of the modern universe, it is subtly altered. When CMB photons enter a massive galaxy cluster, a deep gravitational well, they gain energy, becoming slightly hotter or blue-shifted. As they climb back out, they lose that same amount of energy, becoming cooler or redshifted, and the net effect is zero. But this is only true if the cluster is stationary. If the cluster itself is moving, if it is being pushed by a void, for example, the situation changes. This motion imparts a tiny additional Doppler shift onto the CMB photons scattering off the hot gas within the cluster. This is the kinetic Sunyaev-Zeldovich effect, or KSZ effect. It is an incredibly faint signal, a temperature fluctuation of just a few millionths of a degree, buried in the noise of the CMB itself. For decades, it was a purely theoretical concept far too subtle to detect. But our instruments have finally caught up to our theories. By combining high-resolution maps of the CMB from telescopes like the Atacama Cosmology Telescope and the South Pole Telescope with the vast galaxy catalogues from our surveys, we can now begin to hunt for this effect. The technique is a statistical marvel. We identify the locations of thousands of distant galaxy clusters and then stack the CMB data at those precise locations, averaging them together. Individually, the KSZ signal from any single moving cluster is invisible, lost in the noise, but when you average thousands of them, the random noise cancels out and the coherent signal, the faint hot or cold spot created by their collective motion, begins to emerge from the static. It is like listening for a single specific whisper in a crowded stadium by averaging the recordings from thousands of microphones placed near people all whispering the same secret phrase. This is the ultimate independent test. It doesn't rely on complex distance ladders or assumptions about how galaxies work. It is a direct measurement of mass in motion, a pure probe of the cosmic velocity field. Finding a large-scale coherent KSZ signal that aligns with the outflow predicted by the KBC void model would be the final irrefutable piece of evidence. It would be the universe itself testifying that our entire cosmic region is indeed on the move, pushed by the great emptiness behind us. The quest has therefore become a symphony of observation, a multifaceted, collaborative and intensely competitive endeavour. On one front, the cartographers are refining their maps using the peculiar velocities of countless galaxies to trace the gravitational currents of the local universe. On another, the great space observatories Euclid and Roman are preparing to deliver a flood of data that will dwarf everything that has come before, promising to define the void's structure and its impact with unwavering clarity. And on a third, more esoteric front, cosmologists are sifting through the faint static of creation, hunting for the chaos-seed whispers that betray the motion of entire clusters of galaxies. All of these efforts are converging on a single point in our scientific history. The data is beginning to stream in. The supercomputers are humming, running simulations of unprecedented complexity to compare theory with observation. A generation of scientists holds its breath, standing on the precipice of a discovery that could either beautifully affirm our standard model of cosmology or shatter it into pieces. The evidence is accumulating, the scales are tipping, but the final verdict has not yet been rendered. We are in the courtroom, the arguments have been made, and the jury is about to examine the final decisive pieces of evidence. The answer to one of the deepest riddles in cosmology is no longer a distant dream. It is imminent, and it promises to change our place in the universe forever. And so, we arrive at the edge of our own cosmic shore, looking back at the incredible intellectual odyssey we have undertaken together. We began with a simple, unsettling crack in the foundation of the modern cosmology, a quiet disagreement between two ways of measuring the universe. One method, peering back into the dawn of time, told us a story of a cosmos expanding at a certain stately pace. The other, observing the universe as it is today in our own backyard, painted a picture of a far more hurried, almost frantic expansion. This stubborn discrepancy, the Hubble tension, refused to be explained away. It was not a simple error in measurement, not a rounding mistake, but a persistent gnawing puzzle that hinted at something profoundly wrong, or perhaps profoundly new, in our understanding of everything. We have journeyed through the labyrinth of possible explanations, exploring the shadows where new physics might be lurking. We considered the enigmatic nature of dark energy, questioning whether this mysterious force might be changing over cosmic time, pushing the universe apart with ever-increasing vigour. We entertained the existence of ghostly new particles, fleeting visitors from a hidden sector of physics that might have subtly altered the cosmic recipe in its earliest moments. Each of these ideas represents a monumental shift in our thinking, a bold attempt to rewrite the fundamental rules of reality. Yet even these exotic theories have struggled to fully bridge the gap, to neatly and completely reconcile the ancient universe with the modern one. It was in this landscape of profound uncertainty, amidst this search for the unknown, that a different kind of answer began to take shape. An answer that did not require us to invent new forces or particles, but instead asked us to do something far more radical, to reconsider our own address in the cosmos. This is the genesis of the hypothesis that has been the heart of our story, the audacious Copernican challenging idea of the Keenan-Barger-Cowie void. The proposition is as staggering as it is elegant in its simplicity. What if the Hubble tension is not the result of flawed physics, but rather the consequence of a flawed perspective, our perspective? What if our galaxy, our entire local group, is not situated in an average unremarkable patch of the cosmic web as we have long assumed? What if entirely by chance we find ourselves living inside a colossal bubble, an immense region of space significantly emptier than the surrounding universe? This is the KBC void, a vast basin of cosmic underdensity stretching perhaps 2 billion light-years from edge to edge. It is not a true vacuum, not a hole of absolute nothingness, but a place where the grand tapestry of galaxies is stretched thin, where the concentration of matter is dozens of % below the cosmic mean. From our vantage point deep within this gravitational hollow, our view of the cosmos would be inherently skewed. Imagine yourself at the bottom of a wide, shallow valley. The gravitational pull from the denser, matter-rich cosmic hills beyond the void's edge would be stronger than the pull from the emptier regions within it. This imbalance would create an outflow, a localized cosmic current gently but inexorably, pushing us and our neighboring galaxies away from the void's center and outwards, towards the greater concentrations of mass. This local velocity, this extra push, would be layered on top of the global expansion of space itself. When we look out at nearby galaxies and measure their speed, we would mistakenly attribute this entire outward motion to the Hubble expansion alone. We would calculate a local expansion rate that is artificially inflated higher than the true global value predicted by our measurements of the early universe. The discrepancy, the Hubble tension, would simply dissolve. It becomes an artifact of our peculiar location, a cosmic illusion. This single powerful idea has the potential to solve the crisis without tearing down the entire edifice of the standard model of cosmology. But in resolving one great puzzle, it presents us with another one that touches upon our very sense of place in the universe. For 5 centuries, science has been a story of cosmic demotion. Copernicus moved us from the centre of the solar system. Shapley and Hubble moved our sun from the centre of the galaxy, and our galaxy from the centre of the universe. We have grown comfortable with the idea that we live nowhere special, that the universe on large enough scales is the same everywhere. This is the cosmological principle, a bedrock assumption of homogeneity and isotropy. The KBC void hypothesis forces us to question this comforting mediocrity. It suggests that while the universe at large may be uniform, we happen to occupy one of its grand statistical fluctuations. We are not in a special place in the sense of being cosmically significant, but in a special place in the sense of being statistically atypical. This doesn't necessarily break the cosmological principle, as such voids are predicted to exist within our models of cosmic structure formation. The question is whether a void of this specific size and emptiness positioned exactly where we are is a likely occurrence or a wild improbability. It's a debate that pits the elegance of a solution against the principle of cosmic modesty. And it is crucial for you to understand that this is where the science now stands, on the precipice of confirmation or refutation, in the midst of a vibrant, ongoing and absolutely essential debate. The KBC void is not yet a proven fact. It remains a powerful and compelling hypothesis, one that is being rigorously tested by astronomers around the world. There are those who argue that the evidence for such a vast deep void is still tenuous, that surveys of galaxy distributions do not show an underdensity quite stark enough to fully account for the entire Hubble discrepancy. They point to potential inconsistencies, to the immense challenge of mapping the three-dimensional structure of the universe on such gargantuan scales, where every measurement is fraught with uncertainty and potential bias. They continue to search for answers in the realm of new physics, believing that the tension is a genuine signal from a deeper reality, not just a trick of cosmic geography. This tension between ideas, this clash of evidence and interpretation, is not a sign of failure. It is the signature of a healthy, thriving science. It is in this crucible of skepticism and argument that progress is forged. Every challenge to the KBC void hypothesis forces its proponents to find better evidence, to refine their models, to make more precise predictions. Every new piece of data supporting the void forces its opponents to re-evaluate the limits of the standard cosmological model. This is how we advance, not through sudden singular moments of eureka, but through the slow, painstaking process of building a case of challenging assumptions and of letting the evidence, however strange, be our ultimate guide. Whether the KBC void is eventually crowned as the solution, or whether it falls and is relegated to the history books as a brilliant but incorrect idea, it has already left an indelible mark on cosmology. The very possibility of its existence has profoundly shaped our approach to the field. It has served as a powerful reminder that the universe around us is not a perfectly smooth, idealized fluid, but a lumpy, complex and structured place. The cosmic web, with its dense clusters, long filaments and vast voids, is the fundamental architecture of our reality. The debate has forced us to move beyond simplistic assumptions of uniformity and to develop far more sophisticated tools for analyzing our local cosmic environment. Astronomers are now dedicating immense resources to creating detailed 3D maps of galaxy flows and matter distribution, extending hundreds of millions of light years in every direction. They are no longer just looking out at the distant cosmos. They're conducting a rigorous act of cosmic cartography on our own doorstep, trying to understand the gravitational landscape that shapes our everyday motion through space. This renewed focus on the local universe is a direct legacy of this puzzle. It is a shift in perspective that will yield invaluable insights into galaxy formation and evolution, regardless of the ultimate fate of the void hypothesis. The search for the void has become a journey into the very heart of cosmic structure, and so we look to the horizon to a future brimming with the promise of clarity. Humanity is now building a new generation of cosmic cartographers, extraordinary observatories designed to map the universe with a breadth and precision that was once the stuff of science fiction. On a mountaintop in Chile, the Vera C. Rubin Observatory is preparing for its first light. For a decade, this magnificent instrument will conduct the legacy survey of space and time, scanning the entire visible southern sky every few nights. It will create the deepest, widest movie of the universe ever made, cataloguing billions of galaxies and charting their positions and movements. Its unprecedented data will allow us to construct a 3D map of our local universe of such staggering detail that the existence and properties of the KBC void should be rendered in sharp, undeniable relief. We will be able to see not just infer the true distribution of matter around us, and measure the subtle gravitational currents that guide our cosmic journey. At the same time, orbiting high above the distorting haze of Earth's atmosphere, the Euclid Space Telescope is already embarking on its grand quest. Euclid is a detective of the dark universe meticulously designed to map the geometry of space-time and the evolution of cosmic structures. By measuring the subtle distortions in the light from billions of distant galaxies, a phenomenon known as weak gravitational lensing, Euclid will trace the invisible scaffolding of dark matter, revealing the cosmic web in all its intricate glory. Its observations will test the very foundations of the cosmological principle, determining whether voids as large and empty as the KBC void are a common feature of the cosmos or a statistical anomaly of epic proportions. And following it will be the Nancy Grace Roman Space Telescope, a powerhouse observatory with a field of view 100 times larger than Hubble's. Roman will conduct deep field surveys on an industrial scale, effortlessly capturing vast swathes of the universe in exquisite detail. It will provide another independent and powerful cross-check, giving us the final pieces we need to complete this cosmic puzzle. These are not merely telescopes, they are arbiters of cosmic truth. They are our instruments for putting the KBC void hypothesis, and indeed all competing theories, on trial. The data that will pour down from these observatories in the coming years will be subjected to the most intense scrutiny, analysed by thousands of scientists around the globe. The answer to the Hubble tension is waiting for us encoded in that light. We are on the verge of knowing whether we are truly adrift in a cosmic bubble, or if the explanation lies in a still undiscovered secret of the universe's fundamental nature. Whatever that final answer turns out to be, our journey will have been transformative. This entire scientific saga, born from a subtle tension in our numbers, reveals the true nature of human inquiry. It shows us that science is not a collection of immutable facts, but a living, breathing, and often contentious conversation with nature. It is a process of relentless questioning, of daring to challenge our most cherished assumptions, and of embracing the discomfort of not knowing. The Hubble tension was a loose thread on the grand cosmic tapestry, and in pulling on it, we have been forced to examine the entire fabric of our reality. The KBC void hypothesis represents one of the most profound pulls on that thread, a possibility that recalibrates our place in the universe. It reminds us that even after centuries of looking up at the sky, we are still just beginning to comprehend the sheer scale and complexity of our home. The universe, it seems, is always more intricate, more surprising, and more fascinating than we could have possibly imagined. Our quest for understanding is a journey without a final destination. Each mystery we solve, like the one we have explored here, does not close a book, but merely opens a door to an even larger room, filled with new questions, deeper puzzles, and more breathtaking vistas. The true wonder lies not in having all the answers, but in living in a universe that continues to inspire us to ask the questions, to look deeper, and to never ever stop exploring.